Alright, so we are starting a new unit in this video, sequences and series. Within this video, we are going to do some basic stuff. We're going to define a sequence. You may have studied sequences before, but we're going to look at it in a kind of loose way, and then we'll define it rigorously later. After that, we'll look at some common sequences, and then we'll focus in on two types of sequences, arithmetic and geometric. You may have seen these things before, I understand that, but I wanted to just get it out there, get it out in the open, so that when we start looking at more complicated things later on in future videos, these things are just second nature. So bear with me here. Before I start talking about any of these, I want to share with you a story. There is a famous story that you may have heard before about when Carl Gauss as in Gaussian Elimination, famous mathematician, was in elementary school and primary school. And his teacher asked him to sum the numbers from 1 to 100 probably because all the math he was doing in elementary school was too easy for him, and he was probably being a nuisance to the other students. So the teacher's like, hey, can you sum 1 to 100 while we do the other things that the kids need to learn? And very quickly after he was posed the question, he came back with the answer. And the teacher was kind of flabbergasted, stunned that he was able to solve it so fast. So how did he do that? He did not go 1, 3, 6, 10, 15, 21, 36, 45. He didn't do that. He thought of a roundabout way to solving this problem, and this is what he did. Think about it for a second. Try to think of a methodical way to solve this. But what he did was he looked at this sum. So he's summing these things up. He looked at a new way to write this sum. Another way to write this sum would be to write 100 plus 99 plus 98 plus, what would that be? 2 plus 1. And if you take a second to think about how this is useful, what he did was he added these two equations together. So what's 100 plus 1? That's 101. What's 99 plus 2? Oh, that's 101. 98 plus 3, that's 101. 99 plus 2, that's 101. And 100 plus 1, that's 101. And s plus s, that's 2s. So he determined very quickly that the sum of the digits 1 to 100 is half the sum of the numbers 1 through 100 twice, and the numbers 1 through 100 twice is just 101 times, well, how many of these are there? There are 100 of them. There's 1, 2, 3, 4, all the way up to 100. So 101 times 100, and he was able to do that really quickly. 100 times 100 is 10,000, and then he has one extra 100. So that's what 10,100, and that's not the number he wants. He wants to divide all of these by 2. So he very quickly figured out that the numbers 1 plus 2 plus all the way up to 100 is 10,100 divided by 2. So what is that, 5,050? So we are going to be looking at, with this in mind, sequences and being able to sum up sequences. So here's a sequence, the numbers 1, then 2, then 3, then 4, then 5, up to 100. And the question he just answered was, what is the sum, and I'll talk about this in a second, of the numbers 1 through 100, starting at 1 and ending at 100? 1 plus 2 plus 3, what is that? This is going to be 5,050. All right, so let me briefly explain this symbol right here. This is a sigma. It's a Greek letter. Sigma. And it's the letter that we use to talk about sums. So what this symbol is saying is the sigma indicates sum. We have a product notation as well with a capital pi. But what this sigma symbol is saying is it's saying start with 1 and plug it in. So 1. And then we're going to sum. Now take the next number, 2. And then take the next number, 3, plug it in, you get 3. and then take the next number, 4, plug it in, get 4, and then keep doing that until you get to this number at the top, which sometimes people write n equals 100. So 1 plus 2 plus 3 all the way up to 100, 5050. All right, so that's sigma notation. Let's look at sigma notation one more time. So if I said, hey, let's do sigma notation. So let's sum I equals 1. That's our starting point. Let's go up to like 4 of n times n plus 1. Yeah, let's just stop there. So let's sum the numbers 1 to 4 by plugging them into this. So the first term in my sum is going to be 1 times 1 plus 1. The second term in my sum is going to be, I'm going to plug in a 2 now, so, sorry, not an equals, plus 2 times 2 plus 1. The next term, I'm going to take 3, plug it in, 3 times 3 plus 1. And then I'm going to take the last term, 4 says to terminate, 4 times 4 plus 1. And then what is this thing? Let's see, we got 1 times 2, which is 2, 2 times 3, which is 6, 3 times 4, which is 12, and then 4 times 5, which is 20. And then the final answer here is 20 plus 12, 32, plus 6, 38, 40. Cool. So that's just another example of using sigma notation. It's saying start at this value and constantly plug in integers and then terminate at this value above the sigma letter. All right, so with that said, I want you guys, I'll do it with you, but before I do it, I want you to, let me get rid of that actually. I want you to, in general, find a formula for 1 plus 2 plus 3 plus all the way up to some number n. I want you to find the formula for this. In other words, I want you to tell me what the sum of 1 to n is for any value n. So 1 plus 2 plus 3 plus 4 and stop, 1 plus 2 plus 3 plus all the way up to 100 and stop, or any arbitrary number. So if I wanted to make this 1,000, 10,000, 47. So I want you to guys take a second to try to figure out a formula for this. So I'm going to do it similarly to how Gauss did it. So we have 1 plus 2 plus 3 plus dot, 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 all the way up to, instead of saying 99, 100, I'm going to say the number before n minus 1, and I'm going to say the number n. And I want to figure out what this is, so I'm going to give it a name. I'm going to call it S for sum, and then I'm going to rewrite this sum in a new way. I'm going to write it as n plus n minus 1 plus, I'm not going to write n minus 2, I'm just going to go dot, 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 plus, and then what would this be? This would be 2 plus 1. And then what is the sum of each column of numbers? So S and S, that's going to be 2S. Let me go ahead and maintain the capital S there. And then n plus 1, that's n plus 1. All right, n minus 1 plus 2, that's also n plus 1. Right? 3 plus n minus 2, that's also going to be n plus 1. N minus 1 plus 2, that's also going to be n plus 1. And I've said n plus 1 at least 1, 2, 3, 4, 5 times now. All right, that's going to be n plus 1. Let's make it 6. And then how many of these do I have? That's the new question. Previously, we knew we had 100, but now I have n numbers of them. So how many of these do I have? I have n times n plus 1, and then that is 2s. And then there's our final formula. What is the sum of 1 plus 2 plus 3 all the way up to n? The sum is, divide both sides by 2. N times n plus 1 over 2. All right, there you go. So, big idea here, right? The sum of consecutive integers (1 to n) is, and I'm going to write the sigma notation. We're starting at 1. We're finishing at n, and we're summing just the numbers, not multiplying anything here. It is n times n plus 1 divided by 2. There you go. That is the sum of consecutive integers 1 to n. Yeah, so there you go. That was kind of our warm-up. What I want to look at now is what a sequence is. So what is a sequence? There's a formal definition that we'll talk about later, but the way I want to define sequences right now is just an infinite list of numbers, right? Kind of a lazy definition, right? Specifically, a sequence is an infinite list of numbers. If I'm talking about a finite list of numbers, I'm going to call it a finite sequence. So when I say sequence from now on, you need to interpret that as an infinite number of elements in sequence. All right, so let's motivate some concepts. So let me give you the beginning of a sequence. 3, 5, 7. All right, what is the next number in this sequence? All right, if you said 9, you are wrong. The sequence I had in mind is 3, 5, 7, 11. The sequence of primes. All right, so what does this motivate? This motivates the idea of notation. So it is not sufficient enough to simply list numbers with the ... the ellipses, and hope that someone can interpret what your sequence is. We need some sort of notation that defines what the next element is. So let's look at that. So first off, we use something called subscript notation to define a sequence. So this is going to be a sequence. I'm using these curly brackets around it. And AI is the ith term in the sequence. All right. So what I want you to do right now is understand the difference between a sub I with curly brackets and a sub I without curly brackets. This is the entire sequence. This is an element in the sequence, and it's important to know the difference between those two notation. All right, so if I wanted to describe the sequence of prime numbers, I would probably have to describe it. All right, so here's a sequence, AI. You know what, let me use a different letter. Let's go PI. All right, so PI, where the PI is the ith prime, right? And now there's no misunderstanding this or miscomparing it to another sequence with similar numbers, like the sequence of odd numbers. Right? If I wanted to describe the sequence of odd numbers, let's go ahead and say BI. Right? That is the sequence, right? And BI, well, we can define this explicitly. This is a good moment to bring up what explicit notation is. BI, let's go ahead and say BI is 2i minus 1. So what does this say? It says, well, the first element, B sub 1, is going to be 2 times 1 minus 1, which is 1. All right, and then the second element is going to be, so B2 is going to be 2 times 2 is 4 minus 1, which is 3. All right, so this was B1, this was B2. B3 is going to be, let's plug in 3. 6 minus 1, that's 5. All right, and so on and so forth. All right, so there's two notations for you. You can describe it using words, or you can describe it using an explicit rule. I got one more for you. It is called recursively defining a sequence. All right, here is a recursive sequence that's very popular. Many people have seen this one. Many of you will have seen this. But if I take the sequence 1, 1, 2, 3, 5, 8, 13, 21, ... This is hard to describe. Not impossible, but hard to describe explicitly. But very easy to describe recursively, meaning that if you know a term, do you know the next term? So what is this sequence? This sequence is called, if you have never seen it before, Fibonacci sequence. and take a second to try to figure out what the pattern here is. Right? But if I wanted to define this thing recursively, I would have to go ahead and name the first element 1, name the second element 2, which is in this case 1, and then using these two first elements, I can now define every element in the sequence. Right? The nth element in the sequence, so like 1, 2, 3, 4, 5, 6, the 6th element in the sequence is going to be the previous term plus the term before that. So I've just defined this recursively. You can't give me a number n and then I know what it is, but you can give me the two previous terms. So what would that be? 3 plus 5 is 8. So I know what 3 is, I know what 5 is, I know what 8 is. I know what 3 is because I know its two previous terms. So we needed the first two terms to define this thing, and then every element in this sequence is defined using the two previous terms. This is what we mean by recursive. All right, so let's break out our first arithmetic sequence. We'll talk about what that is in a second. And we're going to talk about that arithmetic sequence either recursively or explicitly. So here is my sequence to use. So I'm going to have the sequence 5, 8, 11, 14, ... What's happening in between each of these? We are adding a number. All right, we could subtract a number, we could add a number, but whether it's adding or subtracting, we call this an arithmetic sequence if we're dealing with a constant difference between successive elements. So if I wanted to define this thing recursively, first I would need to establish the first element. So here's a recursive rule for this arithmetic sequence. We are adding a common difference, right? So the first element is 5, and then some arbitrary element in the sequence is going to be a n, and the way you get it is by taking the previous term and adding 3 to it. So this is a recursive rule because we can't just grab any term we want, but given a term, we can find the next one, right? Or we can look at the explicit rule for this thing, and that would be, okay, so I want a specific element in the sequence, and it's going to be, what would this one be? Let's start with 5, because now if I plug in 1 into this, I'm going to get 5. Yeah, that's what I want right there. I had to think about it for a second. 5 plus 1 minus 1 is 0 times 3. And that's going to be 0, so my first element is 5. But then if I plug in 2 for the second element, I'm going to get 2 minus 1, which is 3. All right, the common difference. And if I plug in 3 for the third element, I'm going to get 3 minus 1, which is 2. 2 times 3 is 6. I'm going to be adding that 3 twice, and I'm going to be getting my term 11 for my third term. So here is our explicit rule. There's our recursive rule. Sometimes we can only define sequences recursively, but it is nice to be able to get an explicit rule. All right, so let me go ahead and write the actual definition of an arithmetic sequence. All right, an arithmetic sequence definition is a sequence in which the difference between successive terms is constant. All right, here is our general arithmetic sequence. All right, we have some term in the sequence is going to be the first term times n minus 1 times that constant difference. This formula here is going to be useful for us as we start to expand upon sequences and start looking at the sum of sequences. All right, that's actually what I want to do next. So what I want you to do is I want you to find a formula for the sum of the first n terms of an arithmetic sequence. So find the sum of the first n terms of an arithmetic sequence. All right, think about how to do that. The first thing I'll do for you is I will write down what the sequence is. So the first term is A. This next term is going to be A plus D. The next term is going to be A plus 2D, A plus 3D, A plus 4D. And then so on and so forth until you get to, not D, sorry, but A times n minus 1D. All right, what is that equal to? Wait, before I move on, actually, I just caught a mistake of mine. We have A plus D plus A plus 2D plus A plus 3D plus A plus ND. There should be a plus right there. So make sure you have that as you move forward. All right, A plus D plus A plus 2D, and so on and so forth. A plus n minus 1D. All right, cool. So I want to, let's do that right now. Let's find the sum of this thing. So we have A plus D plus A plus 2D, right, so on and so forth. I'm going to stop there. What I will do this time actually is I'm going to get A plus n minus 2D, and then the final term is going to be A times n minus 1D. Sorry, I forgot it once again. There's a plus right there. And that's equal to the sum that we're trying to figure out. And I'm going to do this like Gauss. I'm going to flip-flop this and do the exact same thing he did with the numbers 1 to 100. So, A plus n minus 1D. That's my first term. Go ahead and put brackets around it. My next term is A plus n minus 2D. Right, with parentheses like that. And then I'm going to ignore the next one because I know that these are going to sum to the same thing. This is going to be A plus D. And this last term is going to be A. All right, so we need to sum these things. Let me go ahead and put brackets around all these terms up here too. Cool, I'm going to stop there. All right, so if I sum these things, what is A plus n minus 1D? That's 2A. Let me choose a different color. That is 2A plus n minus 1D. Right? And then, right, yeah. And then here we have, once again, 2A. All right, what's D plus n minus 2D? Well, I'm going to have D ends. Okay, that's good. So I'm still going to have and D ends, but I'm going to have negative 2Ds here and 1D here, so negative 1Ds in total. So my first term, 2A plus n minus 1D. My second term, 2A plus n minus 1D. That's what I anticipated. I have the same term appearing multiple times. And then if I jump over here, it's going to be the same thing. I have 2A's, and then I have NDs, but I have negative 2Ds and 1Ds, so I have negative 1Ds, and then same thing here. And I'm clearly running out of room. This is a 2A, this is a 2A. N minus 1 times D. This is equal to 2S. 2S. Sorry, I'm running out of room over here on the side. All right, and how many of these terms do I have? I have 1, 2, 3, 4. I have N of them. I have n minus 1, but we don't want to forget that we're also counting this a, which is kind of like a 0th term. So we have n 2a's and n minus 1 times d's. And that's equal to 2s. And then if we divide by 2, we get our final answer, which is the sum of an arithmetic sequence given an initial term, a constant difference, and the amount of terms is going to be n times 2a plus n minus 1 d all over 2. This can be cleaned up, right, if you think about what we got going on here. All right, I'm going to take this to the next page real quick. All right, we have s is equal to n times 2a plus n minus 1 d all over 2. Right? But if I split the 2a up into a plus a, and I kind of regroup, what is a plus n minus 1d? Right, a plus n minus 1d, that is the nth term. That's a sub n, right? So the sum of an arithmetic sequence is n times a1 plus an, all divided by 2. That's kind of cool. There you go. That is the sum of an arithmetic sequence given the first term, the final term, and the amount of terms. There is no need to actually know the constant difference. Right? And this kind of makes sense because, like, here's a quick example. If I give you 5 plus 8 plus 11 plus 14 plus 17, what that previous statement is saying is the sum of this thing is n times the first term plus the last term divided by 2. Well, what is a1 plus an divided by 2? That's the average of the first and last term. All right, so if I take the average of the first and last term, and then I multiply them by the amount of terms there are, essentially what I'm doing in my example here is 11 plus 11 plus 11 plus 11 plus 11. Right? And each of those 11 accounts for the 5 and the 17, the 8 and the 14, and then the 11 itself. So the sum of an arithmetic sequence is the average of the first and last terms multiplied by the amount of terms. All right, so here's an example for you using what we just discussed here. So example, sticking with that same sequence, 5, 8, 11, so on and so forth. All right, the sequence being this thing. All right, I want you to find, right, that's correct, right? Yeah. I want you to find the sum of the first 13 terms. We're getting used to this new notation here. I could ask you to find the sum of the first I amount of terms. Right? But I want you to find the sum of the first 13 terms here, so go for that. All right, so there's two things you could do here. You could find out what the 13th term is, and then use the average of the first and 13th term, and then multiply that by the amount of terms, 13. Or, since I've given you a1, and you have the constant difference, you could use either formula. So I'm going to go ahead and use the first formula that we talked about. So there's going to be 13 terms, right? 2 times the first term, plus n minus 1, so 12 times 3, the constant difference. This is finding that 13th term, by the way, divided by 2. So what is this thing? All right, so we have 36 plus 10, 46 divided by 2. That's going to be 23, 13. Okay, so let me write that down. 13 times 23, and 13 times 23 is 299. Cool. All right, so that is that. And then if I wanted the ith term, I would just do, sorry, not 13. It would be I times still 2 times 5 plus I minus 1 times 3 all divided by 2. And that is the formula for an arbitrary sum. Here's another type of problem that you might encounter. All right, so take the sequence 3, 10, 17, 24. All right, this is once again an arithmetic sequence. So I could define it for you, but because I'm telling you that it's arithmetic, there's no way to think that this is a different sequence. This is the sequence where I'm adding 7 every single between every single 2 terms. All right, I want you to find out how far in this sequence do you need to go so that the sum is 279. So think about how you might find that. All right, but we want the sum to be 279, and the sum of the first n terms is going to be n times 2a1 plus n minus 1 times, what's the constant difference? 7, all divided by 2, and we want n, and we know what Sn is. It's 279. So what I need you guys to do is just solve this thing. We know what A1 is. It's 3. All right, so solve this equation for me. I'm going to go ahead and do it on the next page. Writing down the wrong equation. I already have that this is 3, so that's going to be a 6. That's a 7. I'm going to distribute. Oh, well, first I'm going to simplify this. So negative 7, 6, that's a minus 1. That's going to be a 7n. And then let's see, let's multiply by 2 on both sides. And let's go ahead and distribute the n as well while we're at it. All right, and then what do we got here? 0 is equal to 7n squared minus n minus 558. So this looks intimidating in terms of factoring. We could use the quadratic formula. But because 7 is prime, this shouldn't be too bad. We have 1 and 7, and 7 and 1. And then we kind of got to think about this. So we got 558 and 1, 279 and 2. I flip-flop the 1 and 7, so I don't need to flip-flop these. 558 divided by, does that 3 go into that? 10 plus 8, 3 goes into 18, yep, so 3 and something. It's going to be, what is that? 186. I'm just going to go ahead and get these last ones with the calculator. 62, 31, and 21. Sorry, 31 and 12. All right, this one is a beast. All right, and if we do a little bit of flip-flopping, we're going to get 7n plus 62. N minus 9. And this cannot be the answer because, as you remember, all of our answers have been integers. So n equals 9 is our solution here. You need to go 9 terms out in order for the sum to be 279. 3, 10, 17, 24. Currently, we're 4 terms out. And then we need to go 9 terms out to get to the answer. So 31, 38, 45, 52. How many I got so far? 1, 2, 3, 4, 5, 6, 7, 8. One more. 59. And those terms should sum to 279. All right, so there you have it. That's arithmetic. The last thing I want to do in this video is talk about geometric. So, what is a geometric series? Geometric sequence. All right, so a geometric sequence. I'm just going to go ahead and throw it out in front of you. The definition of a geometric sequence is a sequence in which the ratio between any term and the previous term is constant. So a sequence where the ratio between consecutive terms is constant. We refer to this constant ratio as r, lowercase r, so r. Similarly to how we used d to talk about the constant difference. Right? R is going to be that constant ratio when we start to define these rules recursively and explicitly. So here's an example of a geometric sequence. All right, let's go with a very common one. We're going to go with 1, 1/2, 1/4, 1/8, 1/16, ... So what is the common ratio between each of these terms? That ratio is 1/2. Right? How do I get from 1/2 to 1/4? Multiply by 1/2. All right, so this is a geometric sequence. And how can I define this thing? If I want to define it recursively, throw V in there. If I want to define it recursively, I need the nth term is the previous term times that constant ratio. And if I want to talk about this thing explicitly, how do I get that? Well, I need to know the first term. In this case, it's 1, and I'm going to multiply that by 1/2. So if I want the nth term, I need the first term, and I'm going to multiply that by 1/2. That gives me the second term. So what do I want to put here? I want to put a n minus 1, because now when I plug in 1, I get 1. When I plug in 2, I get 1 times 1/2, which is 1/2. When I plug in 3, I get 1 times 1/2 squared, which is 1/4. So here's my recursive rule. Sorry, my explicit rule. All right, real quick, a formula for geometric. An example for geometrics. Let's say I know the fourth term in a geometric sequence. Let's say it's 125. And let's say I know the 10th term in the sequence. Let's say it's 125 over 64. What is a methodical way by which I could figure out what this sequence is? Or what if I wanted to know like an arbitrary number in that sequence? Let's go ahead with that. Let's say I want to know what the 14th term in this sequence is. Well, I know that the 10th term is 125 over 64. And I know that it takes me 6 iterations of that constant ratio to get to this from 125. So let's figure out what this ratio is. That's pretty much going to be enough to define this sequence. So 6 of these gets me to 125 over 64. So we need to figure out what R is. All right, a little bit of algebra gets us there. So divide by 125 on both sides. Take the 6th root. R, I believe, is going to be 1/2. And then I can use this to find out what my 14th term is. So how can I find that? Well, I know if I take the 10th term, 125 over 64, and I multiply it by this number 1/2 4 times, I'm going to get to the 14th term. So that's what I want. I have the 10th term, and 1/2 4 times is going to get me to the 14th term. So that is going to be, what is 125 over 64 times 1/2 over 4? 1/2 to the 4. That is going to be 2, 4, 6, 8, 1/8. And 1/8 times 164, that's 1024. So there's our 14th term. Cool. So geometric sequences are actually a little bit easier to work with. But the final thing I want to do in this video is I have a question for you. we've done this with arithmetic. I want you to find the sum of the first n terms of an arbitrary geometric sequence. So, question, challenge, find the sum of the first n terms of a geometric sequence. Right, this is a sum, so real quick, here's the sum notation. All right, your first term up to your nth term of, what is this thing going to look like? Well, you're going to have a first term. We're going to call it a1, and then we are going to have that constant ratio. And so the first term, we want the exponent here to be 0, so the ratio doesn't affect it. So I'm going to go ahead and do I minus 1. So let's see if this is correct. So if I plug in 1, I get the first term times the ratio to the 0th power. So I get the first term. Cool. If I plug in 2, I get the first term times R1 to the first power. So the first term times the ratio. So cool. This is going to work. Awesome. So I want you guys to find the sum of this thing for arbitrary first term, ratio, and amount of terms in sequence. And so let's write this thing out term by term. So we want to find the sum of a1 plus a1 times r plus a1 times r squared plus a1 times r cubed all the way up to a1 times r to the n minus 1. Right, that is going to be our sequence. This is going to be the nth term. All right, so we need to think cleverly like Gauss would. Can we flip-flop this and then sum it? Go ahead and try that if you want. But there's actually, if you've tried that and it failed, there's actually a really sneaky way to do this in a different way than the arithmetic sequence. But I'm going to multiply this whole thing by r. So I'm going to get s times r. I'm going to get a1r. Oh, look, a1r. I'm going to get a1r squared. I'm going to get a1r cubed. Notice that I have similar terms here. And then I'm going to get, my final term is going to be a1r to the n. Cool. And then now what I'm going to do is, I'm actually going to subtract these things, right? I'm going to get s minus sr, and then I'm going to get a1, a1r minus a1r, that's 0. They get canceled out. They get deleted. They get deleted. They get deleted. All these terms get deleted, and then a1r to the n minus 1 minus a1r to the n minus 1, that's going to get deleted, and I'm going to be left with minus a1 to the rn. And with that said, we're pretty much there because we want s. So let's factor out an s. And let's divide by 1 minus r. So s is equal to a1 minus a1 times r to the n, all divided by 1 minus r. If you know the first term, you know how many terms there are, and you know the constant ratio, you can find the sum of a finite sequence of numbers. There's one last thing we can do to that, so wait, let's go ahead and do that. We have a1 minus a1 r to the n all over 1 minus r. We can pull that first term out. So what does this become? 1 minus r to the n over 1 minus r. Cool. All right, so there you go. The sum is that thing. Let's go ahead and use it real quick. All right, so example. I want you to find the sum of the geometric sequence that starts at 10, and then its constant ratio is actually -1/2 this time, right? This one's going to be a little bit different. We're going to go from 0 to 10. So the first term is we're going to call it the 0th term. And this is going to be an I up here. And let's see, what's the first term? Let's just kind of figure out what this is. So we have 10, I believe, right? Because I plug in 0, I get 10 times -1/2 to the 0, 10. The next term is going to be plug in 1. That's going to be -1/2 times 10. That's going to be minus 10 times 1/2. The next term is going to be, I believe, a plus 10 times 1/4, and so on and so forth. The next term is going to be a minus. All right, and we're going to actually have 11 terms here. 1, 2, 3, all the way up to 10. 0 to 10, 11 terms. Right, but we have a formula for this. It is just going to be the first term times 1 minus the -1/2 to the, how many do we want to go out? It's going to be 11 terms out. And then we're going to divide that by 1 minus the -1/2. And this should just pump out the answer. And I'm going to go ahead and use a calculator for this. And I'm getting 6.670. There you go. So if you add 10 and then minus 5 plus 2.5 minus, what would that be? 1.25, so on and so forth. For 11 terms, we're going to sum to 6.670. All right, so there you have it. That's what I wanted to do in this video. I wanted to talk about what a sequence was. I wanted to look at some sequences in practice, and then I wanted to make sure that you guys knew what an arithmetic sequence and a geometric sequence is. Along the way, we looked at some formulas for finding the sum of a finite arithmetic sequence and a finite geometric sequence. Later on, we're going to be looking at the sum of infinite or just regular sequences. So with that said, I'm going to go ahead and close this one out. Have a good day, and I'll see you in the next video.